All right, let's go ahead and get started. So, last time we started taking a look at exponential functions. And exponential functions, as we said, are functions where we are plugging in different things for the exponent. So, x is typically our exponent there. And as we change that exponent, our overall function either grows or decays exponentially. And what that means is that each step in that function is going to be closer and closer together for a decay or further and further apart for a growth. So today we're going to be looking at some real world examples of exponential growth and exponential decay. So, for instance, we have this question right here, taken directly from Hawks. Oh, it looks like I'm not capturing my cursor. Let me fix that for us real quick. All right, there we go. So we have this question right here. Okay, so it says the half-life of nitrogen-16 is approximately 7.13 seconds. Determine A so that A of t equals A sub O, A to the t, describes the amount of nitrogen-16 left after t seconds, where A sub O is the amount of time t equals 0 round to 6 decimal places. Okay, well, that sounds pretty complicated. However, let's break it down, and we'll probably see that it's not as bad as we think it is. So first of all, it says half-life of nitrogen-16. What is a half-life? So you've probably heard of carbon dating before. That has to do with half-lives. And carbon dating is where we can take a look at the amount of carbon-12 and carbon-14 that's in something. You know, all life on Earth is carbon-based. It's going to have carbon in it. And carbon-12 and carbon-14 are the two that we can look at and determine how old something is because we know their half-life. So what is that half-life? Well, what that is the amount of time it takes for a substance to decay to half of its mass. So, for instance, maybe you have a gram of a certain substance and its half-life is 1 hour. That means that in 1 hour, instead of having a gram, you will have half a gram. And it has to do with how the atoms inside of that substance jettison off particles from themselves. And that does happen randomly, but using a half-life, we can kind of predict what it's going to do over a certain amount of time. So we can kind of predict how many of those particles it jettisons over a certain amount of time. Okay, so what this is saying here is that we have nitrogen-16, and it has a half-life of 7.13 seconds. So if we had a gram of nitrogen-16, after 7.13 seconds, we would have half a gram. That is what a half-life is. It's literally half of that substance left from the original. Okay, so what is this asking us down here then? Again, it says determine A so that A of t equals A sub O, A to the t. Well, let's figure out what all of these mean. It does give us some clues. It says t seconds. So t in this function is how many seconds we've gone through. Okay. A sub O is the amount at t equals 0. So if t is time and t equals 0 is how much is left here, then this means A of O is the original amount. So let's start labeling these for ourselves. So again, t is time. Okay, and t of 0, where a of 0, or a sub 0 is the amount of time, is the amount at time t equals 0. Again, that means if no time has passed, this is the amount that we have. So this is the original amount. This is what we are starting with. So a sub 0 is the original amount. Okay. Wait, why are there two M's there? Because it's early in the morning, that's why there's two M's there. Okay. So what else do we have here then? Well, we have A of t, and that says that A of t describes the amount of nitrogen left after t seconds. So this is, what we're trying to find. This is how much is left after we do our function here. So A of t would be the new amount. Okay? And so that just leaves A, the thing that we're trying to find right now in this question. Okay, so we have the original amount, which is A of O. We have the new amount after a certain amount of time. We have T, which is time. So what is A? Okay, well, if we think about it, we need to have some kind of number that tells us how fast this thing actually goes. We know that its half-life is 7.13 seconds, but that's not quite going to be a rate. We need A here, which is going to be our decay constant. Okay, so decay constant is something that we're multiplying this by to get our new amount. Okay, so let's go ahead and try to figure out A. Again, it says determine A so that this describes the amount of nitrogen 16 left after a certain amount of seconds. All right, so how are we going to do this? Well, we know the half-life. We know the half-life is 7.13 seconds. We know that the original amount is A of O. We've got all this information, so we need to start plugging things in. So first of all, we know that after this amount of time, 7.13 seconds, we're going to have half of the original amount. So we have a time, and technically we have a new amount. So what we can say here is that A of t is 1/2 of the original amount. Okay. Then the original amount is right there, A of O, or A sub O, A to the t, which would be 7.13 seconds. Okay, so this says half of this amount here is going to be left over after 7.13 seconds. Again, that's based on our half-life. So can we start figuring things out here? Okay, well, let's try. I know that I can divide a sub o off of both sides because, well, it's multiplying here, so I can divide it off there. And then if I do that, I have to do the same thing to this side. So we have divide by a of o. That cancels there, that also cancels there, leaving us with 1/2 equals a to the 7.13. Okay. So that's nice, but how do we get a by itself now? How do we get this thing off of a? Okay. Well, we could take the 7.13 root of both sides. That would work. Of course, that'd be hard to do without a calculator, wouldn't it? So I'm going to pull up a calculator here. Let's see. Okay. And I still haven't figured out how to get this one to capture correctly, so bear with me. So we've got 1/2 equals a to the 7.13. Again, what we want to do is we want to get this exponent off. So pretend that this was like squared. What would we do to get rid of a square? We'd take a square root. Okay? So we're going to take a root of this side, but not the square root. We're going to take the 7.13 root. Remember that the number in the crook is the type of root we have. Okay. So I'm going to enter that into the calculator that I have here. Okay, there we go. And I am getting, let's see, we need 6 decimal places, I think that says, yeah. 1, 2, 3, 4, 5, 6. So that's zero point 907 3 1 2 3 4 6 0. So there's our A. And again, this is a constant that tells us how the amount changes over a certain amount of time. Again, where we would raise this to a time, like it says here, and then multiply it by the original amount, and that's going to change that original amount to the new amount. So this is a constant that we can use to describe how the amount changes over time. Okay. So I've got another question here that says how much of a 3-gram sample of nitrogen-16 would be remaining after 4 seconds? Alright. Well, we have our formula here, so we just need to plug things in. Again, that formula is A of T equals the original amount, which if we have 3 as our original amount, we'd plug in 3 there, times the constant, which is A, in this case 0.907360. Really don't need that 0 at the end though. To the t. Remember that this is modified by how many seconds there have been. So after 4 seconds, so this is going to be modified by 4 seconds, and this is going to tell us how much we can expect to have gone relative to the original amount. So again, let me just plug this into my calculator real quick, since this isn't exactly easy to do by hand or in the head. So 0.907360 to the 4th power okay, so that's going to give us A of T equals 3 times, let's see, 0.6778 26. Okay. So now there's only one thing left to do, and that is to multiply by 3. So let me just multiply this by 3 here. Okay, and so after 4 seconds, we get A of T, whoops, A of T equals 2.0, round to 3 decimals, so 0.033. Okay, so after 4 seconds, not a whole lot of it has decayed. We've basically gotten rid of 1 of the grams. There's still tiny little bit of that 1st gram remaining, but we're basically at 2 grams now. So not a terrible amount of it has been decayed, but about a third of it has. Okay, so then what about after 10 seconds? Okay, so same thing, except for instead of putting 4 here, we're going to put 10 there. So that's easy to calculate. So, again, same thing. We have A of t is equal to 3, because that's still the original amount that we have, times our constant, which is always going to be this number for our nitrogen 16, and then this time, instead of to the 4th power, it's going to be to the 10th power, because again, that's our time. Okay, so raise that constant to the 10th power. So A of t equals 3 times, let's see, that's going to be 0.37826 378.265, and then multiply that by the 3 grams that we have. And we get an answer of A of t equals 1.135. So even less is left, but now we have, instead of, about a third is gone, much more of it is gone after 10 seconds, which makes sense. I mean, this is a much longer time than we had before, and so we only have about 1 and some change left over. Now, here's a question for us. No matter what, will we ever completely run out of nitrogen 16? So if I were to plug in a huge number here, maybe 500 billion, would we ever run out of nitrogen 16? So I'll pause and let us think about that for a second. Okay. So again, the question that I posed before the pause was, no matter what, after whatever time we let this decay, will we ever run out of nitrogen 16? So even if we plugged in a huge number here, in the billions of seconds, years and years, okay, would we ever run out? Well, if we have 3 original grams, okay, so originally we have 3, we need to multiply these 3 grams by a number that would give us 0 in order for us to have none left over. So this would have to be 0 for us to do that. It doesn't really matter what this number is. Raising it to a power would have to make this 0. You know, this could be 5 in here. Who knows? This could be just any number. But can we raise it to a power to make it 0? Can we raise a number to a power to make it 0? Well, like we said before in last lecture that we had, no. We cannot raise a number to a power to get 0. Raising something to the 0 power makes it 1. Raising something to the negative power just inverts it. It doesn't make it 0, it just makes it a smaller number. Raising something to a positive power just makes it bigger. Okay, so there's no way to make this number here 0, which means that we cannot make the amount of nitrogen 16 that we have left over 0. So no, we will actually never quite run out of it. It'll just keep getting smaller and smaller and smaller and smaller and smaller and approach 0, but it will never quite reach 0. So this is a real-world example of our domain, or really range. So our A of t can never quite get down to 0. So if we were to visualize our graph of this thing, so if we had a graph, it would start, you know, somewhere up here, 3 grams, and curve downward and get closer and closer to 0 without ever actually getting to it. It would never cross this line. Again, that's our range. It's the numbers that y can be. So it starts up here, comes down, never quite get past 0. So our range here would be A of t must be greater than, whoops, not equal to, just greater than 0. We'll never run out of this nitrogen 16. Okay, so let's try another one. So this says the population of a certain inner city area is estimated to be declining according to the model P of t equals 460,000 times e to the negative 0.015 t, where t is the number of years from the present. What does this model predict the population will be in 9 years? Okay. So, let's break this one down as well. If we remember back to our previous example in our model, this right here, P of t, should be our population after a certain amount of time. This number right here would be our original amount. So this is whatever our original population was, or whatever time they recorded this. So 460,000 people. We have t here, and we have e. What is e? Okay, E might be a new idea to y'all. It is called Euler's number. Okay? Euler was a very, very intelligent mathematician. He was also an economist, I believe, but extremely intelligent guy. And he came up with some interesting models for exponential growth and exponential decay, and came up with this number that's kind of like pi. It's irrational. So remember that pi is one of those numbers that just keeps going on and on and on and on and on in its decimals and never repeats. E is very much like that. Generally, though, what we say about E, just like pi is 3.14 generally, E we say is 2.718. Okay? So when we do our calculations, this is the number that we're going to be using for E. Or if you have a calculator that has E on it, use that. Unless otherwise told. Maybe one of these questions will tell you to use this specifically. Any other time I'd be fine with you just using the E button on your calculator. Okay. So what does this model predict the population will be in 9 years? That's easy enough to find out. We just need to plug in 9 for t. So P of t again, this is the population after a certain amount of time, is 460,000 e to the negative 0.015 t. And the t that we're going to plug in here, again, is 9 for 9 years. Okay. So, what do we got here? We've got a power that we need to do. We've got some multiplication we need to do. We've got some multiplication in our power that we need to do. So following our order of operations, we'd really like to know what this power is, because powers are supposed to come, pretty soon on. So let's figure out what this power is. Again, negative 0.015 times 9. And I'm going to use a calculator for that. So negative 0.015 times 9 is going to give me negative 0.135. So now P of t equals 460,000 times e to the negative 0.135. Okay. Okay, so what is actually being raised to a power here? That's important to note. Remember that powers only act on the thing directly next to them. So it's acting on E, not this entire thing. If there are parentheses around this, then yeah, it would be the entire thing. But this is only acting on E. So we need to raise E, this value, to this number. So keep that in mind. Don't multiply this times E and then raise it. Take E, raise it to that power. Just E raised to that power. So let me go ahead and do that. E to the negative 0.135 And I get a result of P of t equals 460,000 times, so e to this number was 0.8737. All right. So just one last thing to do in our order of operations, and that is to multiply 460,000 times this number here. So I'll go ahead and do that. 460,000 times 0.8737. And we get a final population, so P of t, of 401,902 people. So, like the question said, the population of a certain inner city area is estimated to be declining according to a model. Well, is it declining according to this model? Yes. We started with 460,000 people. Again, this is our original amount. And as it declined over how many years? 9? We got to 401,000, about 402,000 in fact. So, yeah, over about a decade, we've lost quite a few people, 58,000 people. Okay, so again, I will pause for any questions we may have. Okay, I'm not seeing any questions, so I will move on. One last one down here somewhere. Where did I put it? My goodness, where is it? There it is. Okay, so this says, in an effort to control vegetation overgrowth 55 rabbits are released in an isolated area free of predators. So this is assuming perfect conditions for these rabbits to breed. After 3 years, it is estimated that the rabbit population has increased to 440 rabbits. Assuming the exponential growth, what will the population be after 9 months? Oh, after another 9 months. I'm sorry about that. Round to the nearest rabbit. Okay. So, first of all, we need a model, and that model is right here. In fact, this model, if you look closely, is pretty familiar, and that is because it is the same model that we used up here. So look at this one. This is original population, I'm sorry, the new population equal to the original population times E to some number times T. This one is also that. New population is equal to the original population times E to some number times T. So what is K? K is a constant. K in this case is the exponential growth constant. Okay, so this is what we're multiplying by T and raising E to get a number we can multiply our original population by to get our new population. Again, it's what's determining how this is changing. Okay. So, again, this says, in an effort to control vegetation growth, 55 rabbits are released in an isolated area free from predators. After 3 years, it's estimated the rabbit population has increased to 440. Assuming exponential population growth, what will the population be after another 9 months? Round to the nearest rabbit. So, we need to figure out some things here. So this is our new population. Okay? So our new population after 3 years is 440 when we had originally 55 rabbits. So let's start plugging those things in here. So, again, our new population is 440. Oh my goodness. Suddenly I can't make fours. Equals. Original population is 55. Times E to the KT. So K, we don't know what K is. And then T is time. That's after 3 years. Okay. So we've got everything plugged in here. The only thing we don't know is K. And really, that's what we want to know. This is our constant, again, that tells us how our growth or decay is happening. It's kind of like the rate, almost. Okay? So we know E, we know our Y of O, our Y sub O, we know our new population, we know our time, we just don't know K. So we've got to figure this out. Well, again, something we can do is we can start solving. So we know that we can divide 55 off of here. That'll cancel. We need to do the same thing to this side, though. So what is 440 divided by 55? And that'll give us 8. Whoops. So 8 equals E to the KT, which is K to the times 3. Okay. Well, we would really like to have K times 3 out of that exponent place. So what do? Is there a process that we can take, just like dividing the 55 off of this side to get kt by itself? Yes. And that's getting into a new idea, and that is logarithms. Okay? So, we will learn a bit more about logarithms next time, but let me introduce this idea to you. E to the kt, we want this by itself, right? So, what we're going to do is we are going to take the natural log of both sides. You might see a button on your calculator that has ln. This is natural log. And we'll learn a little bit more about it next time. But what we're going to do here is we're going to take the natural log of both sides. So we're going to take natural log of 8 and natural log of e to the kt okay? And something we will find with natural logs is that they cancel e. If you take the natural log of e, you get whatever that thing's being raised to. Whatever e's being raised to right now, if you take the natural log of e, you just have this left over. In other words, natural log cancels e. And again, just leaves us with the thing it's being raised to. So, now it's not in that exponent place. Okay. Well, now I can figure out what natural log of 8 is. So I'll plug that into my calculator. And we get a number, it's a big decimal that just keeps going on and on and on. So natural log of 8 is 2.07944. And now we need to divide this side by 3 to get k by itself. So cancels there. Now let's see what this divided by 3 is. So again, I'll plug this into my calculator. And we get a k value. K equals, let's see, 0.69315. So there's our constant. This, again, is telling us how this population changes over time. It's the thing that we're raising e to get this number here we need to multiply our original population by. So now we have all the tools that we need for figuring out what the population is after another 9 months. Now, be careful with this one. Our time is given to us in years. This is months. Okay, so what is 9 months in terms of years? So what we do to convert that is we need to divide. So let's see. whoa, what is that? There we go. If we're given 9 months, and we want to convert it into years, what we do is we take the amount of months and divide it by how many months there are in a year. So 9 divided by 12, that's 75, or 0.75, sorry. Okay. So we want to know what the population is, not after 3 years, but 3 years and 9 months. All right. So we have our original, we have our time, we have our constant, we have everything that we need to figure this out. So our new one, we don't know that. It's going to be our y equals our original, which is 55, times e to the kt, our k, is 0.69315. And our t, again, is 3.75. Okay, so let's figure this one out. First things first, we need to figure out what this exponent actually is. So let's go ahead and calculate that. Again, I'm going to use my calculator to do that. So 3.75 times 0.69315. So now y equals 55 e to the, what is that? 2.5599. Okay, so now we need to raise e to this. So we're going to raise e to that. Again, I'm going to use my calculator. And I'm getting y equals 55 times 13.4545. Man, this is going to be a big bunch of rabbits. Okay. So now I just need to multiply 55 by that. So 55 times 13.4545. Ooh, yeah, that's a lot of rabbits. So our new population is 739.9975. Now the original thing said round to the nearest rabbit, so nearest rabbit here would actually be 740. So just 9 months later, we had 440 after 3 years. Just 9 months later after that, we have 740. That is a lot of rabbits in a short amount of time. That's like 300 rabbits. That's a lot. Okay, so exponential growth. Yeah, again, each step on our exponential growth ladder is further and further away from the previous step. Now again, This is what we're going to be talking about next time, these logs. So we're going to be getting into properties of logs, how they help us solve these things, and some other places that we might see logs pop up. So be prepared for that next time on Wednesday. For now, though, that is all that I have for you. So I hope you have a good day. I will see you later, and goodbye.